We'll just get started. We'll just get started in a couple minutes. Wait for everyone else to come in, and then we'll get started. All right, we can get started. Hopefully, you guys were. I think some of you were here last class, yesterday for sure. So, which is good. And then, as you probably know, today we'll probably just do, like I said last class, mostly just practice problems, a different content and different material. For those of you who weren't here yesterday, we need to briefly go over what we touched on yesterday, and so you are not going to be lost when we start doing the practice problems. Um, so yeah, let me give a quick overview of what we did yesterday. All right, again, welcome to the chemistry part of the program of this week, and this is we first talking about what's covered in this section. So it's the chemical and physical foundations of biological systems. So it's not just chemistry, but also physics, organic, and mostly biochemistry and some biology. So the topics covered in this section, in terms of chemistry, you should probably know all of them. You don't need to go anything like super in depth, like for thermochemistry. You don't need to be like go anything past like the ideal gas equation and stuff like that. But knowing basics of each of these is very important. Some tips, again, try to really understand concepts. Most likely in the MCAT when you go and take it, the passages you probably never have seen them before, or never have don't really know what they're talking about, or specific drug or something you probably never heard of. So it'll be new. So it's always good to understand the concept of it and just memorize stuff. Very commonly, a lot of questions in the chemistry section will probably be like a nomenclature question. So they'll give you either the name, and let's say which one's the compound, or compounds and make you tell what name it is. So identifying compounds and stuff like that. It's a pretty common question. So knowing your prefixes and suffixes are very important. Table on the right. This is important when you're trying to identify compounds that you've probably never seen them before, or try to name compounds as well. Next, so the periodic trends we talked about is really important. Kind of ties in with everything. Ionization energy, the energy needed to remove an electron, always it goes to the right and goes up. It's kind of, in general, you can kind of think about it as the closer the electrons are withheld to the nucleus, the harder it's going to be take electron away. Or you also think about it in terms of stability as well. So the noble gas is all the way to the right, the most stable because they have a filled octet. So they have all 8 electrons in their valence shell. So that's why they're going to be the most stable. And of course, they don't want to remove an electron, otherwise they lose their stability. Atomic radius, as we go down in the periodic table and to the left, it also increases. Right, if you're going down, you're increasing the number of valence shells, or n quantum number, and as that goes there, the atom gets bigger and bigger. And as you go to the right, or go to the left, you can actually increase the radius as well because there's less protons. So as you go right on the periodic table in a row, the number of protons increases. So that's so that means the effective nuclear charge, which is the charge electrons feel from a nucleus, that increases because there's more protons. So the more positive charged nucleus attracts electrons. closer to the nucleus, making a smaller radius. Okay. Quick summary. Talk about the different types of bonds. Talk about ionic bonds, covalent bonds, hydrogen bonds, and atomic bonds. Ionic bonds, where just the electronegativity is too great, and all the way like electronegative atom kind of just take the electron away, not as an electronegative atom, and becomes positively charged or negatively charged. Covalent bonds is more sharing between electrons, and nonpolar and polar depending on if the sharing is equal. Hydrogen bonds is a intermolecular force, the strong intermolecular force between hydrogen and another electronegative atom, and then it's just metallic bonds, which is a sea of electrons. These are your intermolecular forces, the most famous being the hydrogen bond being the most strongest, and it's hydrogen connecting to either oxygen, nitrogen, or fluorine, the three electronegative atoms. Dipole is important as well, just basically between two dipoles. So as you can see, the chlorine and ICl right now has a partial negative charge because it's more electronegative, and the iodine has a partial positive charge because it's less electronegative. Therefore, there's going to be attraction to the partial negative and partial positive. You have your other London dispersion forces, another popular one. So it's also the van der Waals forces. Again, every atom has this, every molecule has this, and just between chance of electrons. The electron cloud is a cloud, and it moves around. It's not static, so it keeps moving and moving. And at any point in time, a certain amount, so the electron cloud might be distributed unequally. So certain, like a lot of electron may be to the right side at one point and have a partial negative charge there. And so it's just random, it's super small, very short-lived, and just random. Amino acids, like I said, is also really important. So that's not only in this section, but also in the biochemical section. They're really tested all over, so it's very important you need to know them. Everything about them, structures, 3-letter codes, 1-letter codes, names, everything will come up and will be tested. Then we talk about hard and soft acid base theory. This is a more niche topic, but kind of ties in a lot of different topics in chemistry. This is what I'm probably going to go over again. So we can do the practice problem that we left off on last time. So again, acids can be hard or soft. Hard are usually small and non-polarizable, and soft is the opposite. This is the characteristic, not physically hard or soft, but hard acids or bases usually are smaller and non-polarizable. Polarizable again meaning the tendency of the electron cloud to be distorted from its normal shape. So you have a big electron cloud, it can be distorted more easily if there's external charge. It can move around more. So that's why smaller atoms are non-polarizable. They're less polarizable. And hard acids and bases have these kind of characteristics. They're small, atomic radii, low polarizability, like I said, high positive charge, high electronegativity, high charge density, high oxidation state. A lot of these kind of just mean the same thing. Like if you have a high oxidation state, like +3, +4, you have a high positive charge, same thing. You probably also have a high charge density. I mean, your charge is very localized, so its charge density is very high. So very similar. High electronegativity, you can also think of it as low polarizability. So fluorine, F minus, has a very low high electronegativity, and thus a very low polarizability as well. And again, hard goes with hard and soft goes with soft. So those hard acids go with hard bases, soft acids go with soft bases. And here on the bottom, you have the common hard and soft metals and acids and bases. And then you have the borderlines. The borderline is the one in the middle. As you can see these trends, right? You can see the hard being smaller, more higher charge, less polarizable, the soft being larger, more polarizable, and not as strongly charged. For example, SCN we talked about yesterday, you draw it out, it actually has resonance. That means negative charge is distributed across the whole molecule. So thus it's not really, it has low charge density, and the density or the charge is not very localized, it's spread out. So it'll be soft, therefore. Good. Any questions on this stuff before we move on? This makes sense. So All right, great. All right, then moving on with some practice problems with this, and we left off on this practice problem, I think. Right, I'm pretty sure it's this one. All right, so let's go over this one then. Recent clinical trials have suggested that 1,3-dicarbonylates offer cytoprotective effects against toxicants of a similar softness or hardness. Research team identified methyl vinyl ketone or butanone as a soft electrophile and 2,5-hexane dione as a hard electrophile. That's which the following, if any, will curcumin offer the best protection. So if you guys got a chance to look at this and work on it, and yeah, we can go over it now. So the first part of it really just is identifying, kind of drawing out these structures. Like, what does 1,3-carbonyl enolate even mean? 1,3-dicarbonyl enolate is the same thing as curcumin. And then the other thing is methyl. It can be a little complicated, like this paragraph. It can be like, what's even asking? But what we really just dissect it. It's very not too hard. It's really saying that 1,3-dicarbonyl enolates offer cytoprotective effects against toxic and similar hardness or softness. And curcumin is a 1,3-dicarbonyl enolate. So that means curcumin will provide protection for the molecules that have similar softness and hardness as curcumin. The first one is probably to identify is curcumin hard or soft. And then after we figure out if curcumin is a hard or soft acid/base, our next step is to first figure out draw what methyl vinyl ketone looks like and what 2,5-hexane dione looks like. And once we draw these structures out, we have to see which one is also soft like curcumin and which one is hard and which one is similar to curcumin, which one is not similar to curcumin. Okay, does that make sense? So I think put these stickers for you. So curcumin is a 1,3-dicarbonyl enolate. If you did not even know that, you could probably assume it from this question because it talks about 1,3-dicarbonyl enolates. So again, 1, 2, 3 is a dicarbonyl right here. Enolate means that it also has this double bond right here in conjugation. So first step, like I said, is to identify if curcumin is hard or soft. Does anyone have an idea if curcumin's hard or soft? What do you think? You can type in the chat. Or you just got here, we're just going over this question right now. You want to have a clue? Okay, so we can look at the structure and we can see first it can have resonance, right? So it can the double bond can move here, it can and put the negative charge on the oxygen. So it has resonance, it has a lot of resonance. You know, the pi electrons are distributed across the whole atom, right? This double bond can go to the right. I don't know if you can see my annotate this right properly. You can see its resonance, right? This double bond can go here. It could this double bond in this. Like these electrons can go on the oxygen and become O minus here. So as resonance there. Same thing here. This double bond can also go here and form resonance structures here. So there's a lot of resonance. And by having resonance, that means the charge, right? This negative on the oxygen is kind of distributed throughout the whole molecule, right? It's not located like this. Oxygen is not bear the negative charge because it can have resonance and get rid of that negative charge. So it's basically there's not very high charge density. It's conjugated means the charge is distributed across a bigger portion of the molecule. Like we talked about before back here, if something has low charge or high charge density is hard. So this one in this case, curcumin has low charge density, because it has resonance, meaning that the charge of electrons are distributed across the bigger atom, bigger space. So curcumin is a soft. So now we have to figure out which one's soft. Is methyl vinyl ketone soft or 2,5-hexane dione soft? And as you can see, the methyl vinyl ketone is probably the best answer because it's the same thing as curcumin, stickioenolate. So this again, the double bond can go here, and the oxygen can bear that negative charge because due to resonance, it can bear this negative charge. And thus it is also soft because it has resonance and the charge is distributed across the whole atom. Does that make sense? Any questions? This is a little trickier one. All right, makes sense. Okay, hopefully that wasn't terrible. Let me just get rid of that. Yeah. Next, we have this question. That's another question that also kind of ties in a little bit of biochemistry, which is important as well. Okay, sweet. So, question is how you look at these two reactions right here. On top, and it gives you the equilibrium constant for each. Oh, sorry. This is the equilibrium constant for each. So yeah, you can just see what the equilibrium constant is. So the top one's 4.5 times 10 to the negative 2, and the bottom one's 4.2 times 10 to the negative 15. Question states, how does the hard-soft acid-base theory account for the difference in KQ, or the equilibrium constant values for the two ligand exchange reactions given in the passage? So again, the equilibrium constant is calculated like this. So where it goes products over reactants raised to their number up front. Okay. So I'll give you guys a couple minutes to look over this and kind of think about it, and then we'll go over it soon. And yeah, let me know if you have any more questions. All right, you get a chance to look over this. You guys ready to go over it? Any more time? Okay, perfect. See one thumbs up, so all right, we should be good. Okay, so do you have an idea how to start, how they approached it? Let me go over. Okay, so and for looking at this first, we look at the equilibrium constant. So top reaction has a pretty low equilibrium constant, which kind of tells us that this ratio is heavier on the bottom. That means it favors the reactants. So how the bottom reaction has a pretty high equilibrium constant, meaning the ratio favors the products. So we know that the bottom one favors the products and the top one favors the reactants. Now, why is this? We gotta use hard acid base theory so we can think of these as ions and kind of see which is soft, which is hard. So right here you can see it being, so we can see first of all the top one, the reactants are being favored. That means HF is being favored, and mercury, methyl mercury with water, that ion is being favored. While on the bottom, the product is being favored. So bromine with methyl mercury is favored, and then H with water is favored. So hydrogen with water is favored. So again, soft goes to soft and hard goes to hard. So choice A says H or Sg plus and F minus are hard ions and favorably bind together to form an ionic compound. So that's not true. As you can see in the top reaction, when mercury and fluorine combine together, that's a product. And again, products are not favored in this top reaction. That means that's not true, right? Because mercury, this is this, and this is not favored. It's a product and it's not favored because the equilibrium constant is so low. That's not right. Mercury and fluorine are soft ions and cannot form covalent bond in solution. That's not true. Again, fluorine is a hard ion because it's very electronegative. And high charge density, very low polarizability. It's a small ion. If you look at back our periodic trend, so that's not true at all. Hg and Br do not match in terms of our hardness. So let's look at the bottom. Hg and Br are right here. They are right here in terms of this product. Again, this is a product of this reaction, and the product is actually favored. Looking at the equilibrium constant, the equilibrium constant is so high, so we know that the mercury and Br minus do match because it's favored. And in this case, they're actually both soft ions. But you don't even need to know that. For this part, you can just say because their products and products are favored, they do match in terms of their hard. They must match in terms of their hardness. Next, we can look at D. So D is probably the right answer here. Ag and B plus are soft ions. They prefer to bind, forming a bond covalent in nature. So D is the correct answer. They are soft ions, and then they form a bond that is covalent in nature. Or any questions there? That makes sense for the most part. How we got D the answer. And again, they're soft because they're larger ions, more polarizable. They have a bigger electron cloud. They're not super charged. They're big, and charges are more distributed over the atom. Or any questions on that before we move on? Yeah. Right. If not, we're gonna move on to something different a little bit here. So we're gonna move on to NMR. I'm talking about spectroscopy for a little bit. So NMR and IR. It's the remaining portion of this lecture or this class. So it's all through Khan Academy. If you can give a quick read through of this passage, it's not going to be super relevant to this question, but it's a good passage to read and kind of get familiar with it just to see what we're talking about. But I'll post in the chat. I'll give you guys like 5-10 minutes to just read it, and then we'll go over the first question, which is about NMR matching this NMR spectra to any of these molecules. Okay. Put it in the chat for you guys. All right. So go ahead and give that a quick read. And then we'll come back and discuss the first question. But go ahead. You can try, yeah, go read this and try to answer the first question by yourself. Try to see if you get an answer. And then we'll come back and kind of dissect it. This one's a little tricky. Hopefully you know your NMR peaks and stuff like that. But yeah, so go ahead. I'll give you guys a good amount of time for this to read and answer the first question. Yeah, let me know if you have any questions. Sound good? All right. You know, if you just came in, we're just we're just reading this passage from Khan Academy and going over and doing the first question or attending to the first question. Again, if you just came, we're just going over this passage, and if you can answer the first question, that would be great. And read it. And just give me a thumbs up when you guys have read it, and we'll move on. All right, looks like we're done. We can move on. Does anyone have an idea what the answer might be? We go over it. All right, can be a little tricky instead of NMR if you're not very used. If you haven't memorized NMR yet, if you haven't been used to it. Basically, the question is using this NMR shown here to the right. What is the what molecule 1 through 7 is a match to? And again, if you just read this NMR, if this moves more to the left, that's moving downfield. That means it's de-shielded. So, if you're have a molecule that's high, if you have a molecule of hydrogen that's close to like a electronegative atom, for example, like chlorine, for example, like HCl, that would be very much to the left because it'll be de-shielded. The chlorine will pull the electron density away from the hydrogen and make it more accessible for the rate for the beams to um hit the hydrogen. And the right is shielded. So if you're um very shielded or not have any electronegative atoms around you, you can move to the right. So as you can see here, there's a multiplet at 5.25, and we have a couple things at 7. Before we go dissect this, we can look more at this is the molecule, but we can look more at what you really need to know for NMR. Let's just go over this first, I think. So this is a bottom left. You can see kind of the made popular peaks and where they come at. You should definitely know these. The carboxylic acid are very much to the left. Again, that's because the hydrogen is very de-shielded right next to oxygen. The oxygen is super electronegative, so it's very de-shielded. So you see anything 11 or 12, it comes right down there. Aldehydes come just below around 10 or 9, and they're very quite also de-shielded as well. Your aromatics around 7 and 8 around where the aromatic means. That's your aromatic protons. Remember, each ring has protons on it, so it's gonna be a multiplet. So it's gonna be very because there's gonna be a hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here. They're all kind of different environments, so they're gonna each have their own peak, and because they're with so many different hydrogens around them, they're kind of gonna be split off one another. Your alkenes are gonna be here, and you have your OH and NH. Those usually don't come up, and they're gonna be like a broad peak. you see a broad peak around 4-ish, it's probably a OH. And then you can see your carbonyls, your alkyl shell. So CH is your CH with a bond to a carbonyl. All these like second degree alkyl chain, second degree. So CH3, CH2, CH are all going to come around very early, so around the 1 to 2. And again, as your splitting pattern that you should probably know, you got your singlet. If it's no hydrogen, it's the N+1 rule. So you have this is N+1 splitting rule. So if you have one neighboring hydrogen, you'll be a doublet, triplet, quartet, exact, etc. And to the bottom right, you see a more detailed chain, a more detailed type of chemical shift with each different type of hydrogen species. Okay, now let's go back and analyze this real quick. I just gave you kind of the peaks, but let's go kind of see why each peak kind of lines up. I don't know. Yeah. So you see here that first we have something around 7. So it's probably gonna be an aromatic peaks, right? So you have all these are aromatics. That's gonna be right your 7 range right here. And it's gonna be multiple peaks because there's multiple hydrogens in different environments. I think the really good one to look at for here is you see 1 and 2, for example. 1, 2, even 4 and 5. 1, 2, 4, 5, if you can see. So for example, 2. So 1 has a carboxylic acid. And we know if it's a carboxylic acid, that's going to come all the way down to the 12 and 13 range, all the way down here. And we don't see any peaks like that. So it's probably not going to be a carboxylic acid. 2 is an aldehyde. Again, aldehyde comes around the 9 and 10 region. We don't see any peaks there. Not aldehyde. It's not going to be 1 or 2. Same thing with 3. It's a carboxylic acid. So these are very not going to be that. Not going to be 4 because there's going to be a carboxylic acid again. So it's kind of helpful if you just like pick the main peaks and kind of see if they have the main peaks there. So carboxylic acid peak, we know it's know how to identify it. So it kind of eliminates 4 options. 4 of the 7 we can eliminate because they either have an aldehyde or a carboxylic acid, and we don't see those peaks either here. So really we're only between 5, 6, and 7 here as the right answer. One other thing you can look for is that 5 and 7 have an OH group, and so they will probably have these OH peaks. We don't see any OH peaks here. We see around 3 or 4. There's one peak around here, but it's not going to be a broad peak. Again, the OH peak would be broad and low. It'd be a smaller peak and be low and be broad. We don't see that peak here, so probably not either 5 or 6 or 5 or 6 either, because it's probably going to be no OH peak. So that's that. I know in real life you don't really see the OH peak in NMR spectra. If you run it, if you ever run one before in lab, it's hard to pick up. But the MCAT will probably put it on there, and it's not going to be like an actual spectra. They're going to just probably put it on there for you guys. So it's not going to so it's going to probably have an OH peak there. But if you even look closer, you see these 6.4 peaks right here. These 2 hydrogens will be also have peaks here. You know your OCH3 bonding to oxygen. That's gonna come around 3 again right here. That's this peak right here, because you know that those CH3s come around here, around 1 and 2, and because it's bonded to oxygen, it's a very electronegative atom. It's gonna be shifted to the right. So it's just shifted to the left because it's gonna be an OMe, so it's gonna be the CH3s bonded to this carbon bonded to oxygen. It's electronegative, so it's gonna be more deshielding. So even though this usually comes around 1 and 2 CH3s, it'll actually be shifted to the left. Okay, and then the other peaks are your other yeah, these are the kind of peaks around here. Hopefully that made more sense. Yeah, I don't know if you have any questions about that, but I know it's a little tricky, but like knowing your NMR well, knowing the main peaks can really help come test it. Or any questions? Right now, let's go talk about IR real quick. These are the IR peaks that you guys should know. These are the major peaks. IR, again, it's infrared spectroscopy, so it's basically you shine IR lights on an organic compound, and this causes the bonds to stretch and bend. And we can analyze which wavelengths or energy are absorbed by each compound and help diagnose different functional groups. So different functional groups like carboxylic acids, triple bonds, amides, amines have stretch different. So the bond can stretch differently when exposed um, light. So it can or in or IR lights, so infrared lights, they can bend or stretch differently. So stretching is really happening around here after 1500. Between the 500 and 1000 range, that's basically called the fingerprint region. So that's basically where the bending occurs. So bending usually happens at lower wave numbers than higher wave numbers. That's when bending occurs. And a fingerprint region is called a fingerprint region because it's unique for each compound. Can really help you kind of distinguish compounds, and that's what's called a fingerprint because it can help you. It's unique for different compounds. It can help you distinguish between different compounds. But if you're not just looking for if you have like carboxylic acid, if you have a general structure for a compound, you can use stretches as well. It's also important to know you kind of relate this to like light. So wave number is on the x-axis. I mean, you should know that wave number is the inverse of wavelength. So 1 over wavelength is wave number. And wavelength, you can kind of think about it, right? A higher wave number means a high wavelength. So if you have a stronger bond, for example, like a C triple bond to N or C triple bond to carbon. So these are triple bonds, as you guys probably know, are stronger than double bonds or single bonds. So if you have such a strong bond, triple bond, you probably need more energy, more light energy to stretch that bond. Thus, as you move to the right, we get to stronger bonds, like a triple bonds and random bonds, because we need a lower wave number means lower wavelength of light, and lower wavelength means higher energy of light. So higher energy of light is needed to stretch these bonds or get these bonds to stretch because they're stronger. That's why they have a lower wave number. So that's also important to keep in mind and draw that connection there because it's an important connection to draw. Besides that, yeah, so these are structures, your NH starts comes here. Always again, it's like a little broad alkene, alkyl statuses, carbonyls, and like important ones are like around the 3000 range, your OH, and 1750 is very common for carbonyls. Carbs, so carbon double bond to oxygen, so your carbonyl, that's gonna come around 1750. That's very important. It's probably the most famous one. It's either you have like a carbo, either if you have something around 1750 around this range, you probably have carbon double bond to oxygen. Okay, let's just do a quick practice. Let's see how much time we have left. Okay, so I'm gonna do this practice. So do this practice problem, and I'll check in real quick. I'll give you guys like a couple minutes to do it, and then we can go over it. In the meantime, I'll try to grab my charger. Okay. All right, so it's sake of time, we'll just go over this. Any questions on this? Um, yeah, let's just go through it. All the in short, so which of the following statements accurately describes the molecular vibrations characteristics of IR spectroscopy? So A, stretching frequencies are lower than corresponding bending frequencies. So again, you can think about frequencies here, but it's kind of similar to wave number. So if you have a higher frequency, that means you have a lower, higher wavelength as well. So that means you need more, higher frequencies, more energy as well. So stretching basically it corresponds to higher, more, no, if you have a higher frequency, you have a shorter wavelength. So yeah, sorry about that. If you have a higher frequency of shorter wavelength, and this is more energy. So the stretching take basically more energy, or take stretching is lower in energy than bending. So we can go back here. It's not the case because bending happens in the fingerprint region, as I talked about. Now it's going to be the most energy because the wave number is so high. That means it's going to be of a higher frequency, higher energy to bend molecule rather than stretch it. So this is false. Stretching frequencies are lower than corresponding. Actually, no, wait, sorry, yes, this is right. Stretching frequencies are lower than corresponding bending frequencies. Yeah, that is true. Okay, B. Triple bonds have lower stretching frequencies than corresponding double bonds, which have lower frequencies than single bonds. Triple bonds have lower stretching frequencies than this is false, right? Triple bonds are going to be stronger than double bonds, so that's they're going to have a higher frequency in order to stretch them. So this is false. Bonds to hydrogen have higher stretching frequency than those that heavier atoms. Let's go back here. Higher frequency than those that heavier atoms. That could be true. The OH is around 3,000. D, stretching frequencies appear mostly in the fingerprint region. That's not true. Because stretching again it happens. Fingerprint region is where the bending happens. So stretching frequencies are lower than corresponding. All right, so the best answer is probably A. Let's double check that's right. I'm missing something. Yeah, I think the best answer would be A. In this case, I can double check. Let's see. I missed anything here? So that's actually not true. Okay, so let's look. Actually, the right answer is the hydrogen one. So C. Let's see why though. Yeah, so stretching actually happens at higher frequencies. Um, that is actually true. Yeah. And then it's the hydrogen. So yeah, basically I use elimination. So yeah, frequency. Sorry, the minute got confusing. But yeah, so right answer is C here, that the stretching frequencies are lower than corresponding bending frequencies. And you just go back to this with wave number and seeing how it's so bending is occurs around this wave number. So shorter wavelength, shorter wavelength means more energy needed. So yeah, you can think about it that way as well. And yeah, so A is right. So the best answer here is C. We have 2 minutes left. I have one more question we can do. You can take a look at this real quick. I'll just tell you. You can try, yeah, just try to work on this in the last minute or so, and then I'll just tell you guys the answer. You guys can look at it yourself after the class. So basically, there's plots and basically which one is right, and you kind of look at the plot, and you first see there's a big difference around this 3,500, maybe I think. There's a big broad peak. Again, that's the OH bond. That's the bond there. So you can probably off the bat say one of these has hydrogen bonding, so OH, and the other one does not. And the best answer for that would be due to solvent. because the solvent can probably hydrogen bond depending on what solvent you're in. Okay, hopefully that makes sense. And you can also look at this yourself and look at the Khan Academy. That's where I got all this stuff from. And yeah, I think we're just about out of time. Any last minute questions on chemistry before we conclude? All right, if not, thanks, guys. I'll see you tomorrow, I think, for the group studies session. Yeah, thanks.
Thanks.